The remainder I'll let you do as a problem set. This is the spirit of the whole calculation. But in d dimensions, you have to work a little bit more because this is a d-dimensional thing, this is d-dimensional thing, and every time you take derivative, you'll get d by d matrix. So I'll just tell you what it looks like in d dimensions. Jacobian, d-dimensional version of the slope. Japanese world, computed at a fixed point. You came back, and this is a fixed. The Jacobian that you computed in your coordinate, xq, so not tilde here, just Jacobian. And then this guy here turns out to be a matrix of derivatives, so I'll give it some, I don't know why, but in book I call it gamma. And it's computed at f of x. So this is a matrix aj, this is al, this is l, m, and then there is inverse of this matrix gm at mj, summed over l's and m's. General statement is quite useful. So this is how any finite time Jacobian transforms if you start at point x and you go some time t, or in the new coordinates you start at the image of x and go time t. That finite time says that you have to compensate for the initial point here, and then you have to you pick up a term of, this is from inverse mapping, and then you pick up the term of where the final point is along this trajectory. You have to go to y coordinates. You give me your flow, you give me your transformation h. I can compute matrix is the new coordinate, the old coordinate, or if you wish, you can write it as h of x to make it more explicit. And the other one, which is d of inverse operation of y divided by dy. You do curvilinear transformation, but locally you just keep the linear part of it. So you go from the coordinates in Japan to coordinates in Georgia. You compute the linear deformation of your neighborhood in Georgia. The result is a point along the trajectory time t later. You reconvert this using the derivatives to linear approximation derivatives, and you get Jacobian in new coordinates. If f of t, let's call it this, f of t of x is x, so this is equilibrium or fixed point, then this is being evaluated at the initial point because I came back. And in that case I have that the g minus 1 is inverse of g because it's matrix evaluated at the same point. That means I have a similarity transformations. So one way to compute eigenvalues is to take your matrix and solve the eigenvalue problem. I'm allowed to multiply this by 1, so I'm allowed to write this as determinant of d by d matrix times its inverse times j minus lambda I. That's just multiplying by 1. Then I'm allowed to use cyclic property of determinants and traces to write this as determinant. On the similarity transformation, you'll get the same spectrum. The multipliers I are invariant. The reason why I emphasize it now is because once we get to periodic orbit theory, one of the beautiful things about it is that all averages we compute will not be in our coordinate system. They'll actually use this invariant quantities. So it doesn't matter what coordinates you use to compute your data. The final calculation of giving predictions from the data will be coordinate independent.